Swayam Prabha. Digital India. Educated India.
So, today we will continue our discussion on flow mode analysis of electro and magneto-rheological fluids. In the last lecture, we did the analysis considering the fact that there is no applied electric or magnetic field, and today we will discuss about what happens when there is a magnetic field or electric field applied, like what is shown here. And in the last class, towards the end, we saw that because the shear stress is close to 0 near the mid zone. So, there is always a region here where I have no strain rate, shear strain rate. So, this part the thickness of which is delta, that behaves like a solid. So, it just moves as it is without any shear strain rate. Now, the other two part, the above this region of delta thickness, that part has shear strain rate, and the below part also has a shear strain rate. So, we divide this entire zone into three parts, maybe zone 1, zone 2 and zone 3. Now, because of the symmetric nature of the problem, this zone 2 is placed symmetrically. So, based on the dimensions, we can say that the thickness of zone 1 is d minus delta by 2 and thickness of zone 3 is also d minus delta by 2, and that tells me that the value of y 1 is d minus delta by 2, and accordingly I can find the value of y 2, difference between this point, and that is d plus delta by 2. So, we have discussed the boundary conditions also. At these two plates we have no slip boundary condition, and at the two ends of this mid region we have strain rate as 0. Now, based on these boundary conditions we can analyze the flow. Now, we have three regions and we have to look at the behavior separately. So, let us look into region 1. In region 1, again our governing differential equation is mu del 2u by del y 2 is equal to minus of del p by L, and then if we integrate that, that gives me u1 of y. If we just integrate it twice, that gives us two constants, and finally it comes as C2. So, there are two constants, and these two constants can be evaluated by putting the condition that at y equal to 0 u is 0, and at y equal to 1 del u by del y is 0. So, at y equal to 0 we have u1 equal to 0, and that tells me that C2 equal to 0, and then at y equal to y1 we have del u1 by del y, which is evaluated at y equal to y1 is equal to 0. That tells me that C1 equal to delta p y1 by mu L. So, just to show it, we have del u by del y equal to minus delta P L y by mu plus C 1. So, in this expression when I put y equal to y 1 and the left hand side as 0, C 1 comes out. So, that shows me a profile of the velocity along the thickness in region 1. So, we can write that as u 1 as a function of y becomes minus del t del p by 2 mu L y square plus del p y 1 by mu L y, and then the same thing can be represented as del p by 2 mu L multiplied by y into d minus delta minus y, because we know y 1 in terms of d and delta, or this is also del p by 2 mu L multiplied by y into 2 y 1 minus y. So, y 1 is del d minus delta by 2. So, it is 2 y. Then now let us go to region 3. In region 3 we can just say that the flow profile would look symmetric, but still we can derive that. So, in region 3 if we denote the velocity as u 3, so u 3 1 becomes minus del p by 2 mu L y square plus C 3 y plus C 4, or we can say del u by del 4, but del u 3 by del y we are not evaluating it anywhere, we are just writing the expression. So, del u 3 by del y is equal to minus delta p by mu L y plus C 3. Now, again we would do the same set of exercise to find out C 3 and C 4. So, here we apply the condition that strain rate del u 3 by del y evaluated at y equal to y 2 is 0, and that tells me that C 3 is equal to del p y 2 by mu L, and then we can put the other boundary condition which is u 3 which is evaluated at d, and that is, if we do it we get the expression like this, del p by minus del p by 2 mu L into d square plus del p by mu L into dy 2 plus C 4 equal to 0, and that helps me finding out C 4 as del p by 2 mu L d into d minus 2 by 2. So, if we plot the velocity profile, we would see that the value is 0 here and it goes up and gets some value, and again the value is 0 here, and if y reduces it gets the same value at y equal to y 2. Now, we have to just ensure that if we evaluate u 1 at y equal to y 1, we get the same velocity when we evaluate u 3 at y equal to y 2. So, before doing that, let us write down the final expression for u 3 after applying all the constants, and the expression becomes minus del P by 2 mu L y square plus del P by mu L y 2 plus del P by 2 mu L d square minus 2 d y 2, and on simplifying the relation the expression comes as del P by 2 mu L multiplied by d minus y multiplied by y minus delta. Now, let us evaluate those velocities at y equal to y 1 considering u 1 and at y equal to y 3 considering u 2. So, that would give me the velocity at which the region 2 travels. So, region 2. So, if we evaluate u 1 at y 1, that comes as delta P by 2 mu L multiplied by y square, and this again can be written as delta P by 8 mu L multiplied by d minus delta square. Similarly, u 3 at y 2, if we evaluate, that comes as delta P by 2 mu L multiplied by d minus y 2 multiplied by y 2 minus delta, and that is delta P by 8 mu L multiplied by d minus delta square. So, that shows us that u 1 at y 1 is equal to u 3 at y 3 is equal to some velocity, we call it u p. So, now if we plot the velocity profile, and this is our region with thickness delta. So, the velocity is 0 and 0 here, and the velocity increases and gets a value u p, and here also the velocity increases and the value is u p, and this u p is maintained in the region, in the mid region, in region 2. So, region 1, region 2, region 3. Now, this constant velocity u p u 1 u 3 equal to 0. Now, this constant velocity u p is the velocity at which the mid region travels, and that is called a plug region. So, this region, as we said, there is no velocity gradient. So, that travels as a solid with one velocity. So, that is called the plug region. So, we can call it region 2 is known as plug region. Now, that we know the velocity of the plug region, we have to find out the thickness delta of this region. Now, to do that, first we solve the governing differential once again in terms of shear stress, and that helps us doing that. Now, we know that we have del 2 y by del y is equal to minus del P by L, that is the differential equation that in terms of the shear, and del 2 is the shear stress in region 2. So, if we solve the equation, that gives me del 2 as a function of y is minus del P by L into y plus C 5. Now, we have to evaluate C 5 first. So, for that again we apply the boundary conditions. If we evaluate this del 2 at y equal to y 1, it should be equal to the yield stress, because immediately below this y equal to y 1 the yield stress, the stress is more than the yield stress. So, in this region, so at here the stress is yield stress equal to yield stress, and here the stress is equal to the negative of the yield stress, because here we can see that the velocity gradient is positive, here the velocity gradient is negative. So, here in this region tau 2, we can say tau 2 y 2 equal to minus of tau y, and here we can say tau 2 y 1 equal to tau y. So, we have to put these two boundary conditions. If we do that, we can write that at y equal to y 1 we have tau 2 equal to minus delta p by L into y 1 plus C 5, and we also have at y equal to y 2. All right. So, it is not, this value is now tau y, the yield stress. So, it is tau y, and here we have minus of tau y equal to minus of delta p by L into y 2 plus C 5. So, if we add these two equations, then this gives me C 5 as delta p by 2 L multiplied by y 1 plus y 2. If we just add these two equations, then tau y's cancel each other, and we have 2 C 5 here, and finally solving that we get this. And again that tells me that if we put that same value, then tau 2 y. So, if we put that same value of C 5 here, then we get tau 2 y is equal to minus del p by L into y plus, so we get tau 2 of y is equal to minus del p by L into y plus del p by 2 L multiplied by y 1 plus y 2, and we know that y 1 plus y 2 is d, because our y 1 is d minus delta by 2 and y 2 is d plus delta by 2. If we add them, we get d. So, we have d. So, again this expression can be written as del p by 2 L into d minus 2 y. So, that is the expression of shear strain in the region, shear stress in the region, in the plug region. Next, we have to find out delta. So, for that what we can do is we can put the value of this tau 2 y at any of y, maybe y 1 or y 3 at any of the boundaries, and from there we can find the value of either y 1 or y 2. If we know y 1 or y 2, we can find out delta. So, let us write at y equal to y 1, we can write minus del p by L plus del p multiplied by d by 2 L equal to tau y, and from here, so here it is evaluated y equal to y 1. So, y 1 should be there, and finally, after simplifying we know that this quantity y 1 is d minus delta by 2. So, finally, after solving we can find out delta, the plug thickness, and that comes as tau y multiplied by 2 L divided by delta p. Then we can define a non-dimensional quantity del by d. So, the plug thickness divided by the total thickness of the region, and that comes as tau y multiplied by 2 L divided by delta p and d, and let us call that delta bar. So, that is a non-dimensional quantity. Now, from here we can see that when this non-dimensional quantity is 1, That means, the entire region, in the entire region there is no shear flow. That means, the entire region is in the pre-yield region. In other words, we can say that if tau y is greater than delta p d by 2 L, when tau y is greater than delta p by 2 L. So, that denotes that delta is 1, which means that in that yield stress there is no flow possible. That means, if I want to, if I am given the pressure difference, and then if I want to close the flow by the valve action, then I have to put an electric or magnetic field in such a way that we at least get this amount of tau I, and that blocks the entire flow. Now, we have to find out the equivalent damping, and for finding out the equivalent damping we would proceed with the same, and for finding out the equivalent damping we would proceed with the same approach. So, we will assume that there is an equivalent velocity u m maybe, and we will find out the flow corresponding to that in terms of u n, and then we will find out the actual flow, and then we equate both the terms, and that would give me u m. Now, again if we write once again, we have these two plates, x, y, z, and this is our d, and we say that the dimension in the z direction is b. So, if the equivalent velocity is u m, then flow rate is equal to u m multiplied by b multiplied by d, and we have to now equate that with the actual flow. So, the flow actual is q is equal to 2 q 1 plus q 2. Again there are 3 regions, region 1, region 2, region 3. So, the flow in region 1 is q 1, flow in region 1 is q 3, and if I add those two up, I get the summation as 2 q 1, because q 1 and q 3 are same, because these two regions are symmetric. So, q 1 and q 3 are same. So, these two regions give me a flow of 2 q 1, and q 2 is different, that gives me a flow of q 2, and their total is the total actual flow. So, to find this out, we perform integration from 0 to y 1, and then we multiply here y 1 of y, and then we multiply that quantity by b, and then we integrate from 0 to y 1, and then for q 2 I just need u m, sorry not u m, that is the u p, the plug flow here, plug velocity u p multiplied by the cross section dimension, that is delta multiplied by b. So, if we evaluate this quantity, finally the quantity becomes delta p b by 12 mu L multiplied by d minus delta cube plus we have delta p b by 8 mu L multiplied by d minus delta square delta. So, that is the total flow q, and this should be equated with mu m b d, and then once we do that we get, sorry, it is not mu m, it is u m. So, once we do that we get u m as delta p d square 12 mu L multiplied by 1 minus delta bar square. Delta bar is this quantity, the non-dimensionalized plug thickness, multiplied by 1 plus delta bar by 2. So, that is the equivalent flow throughout the passage. Now, that we have got the equivalent flow, we can find out the damping coefficient. So, the total force is delta P B D, pressure multiplied by the area, and here we are using the suffix A to denote that it is in active mode. So, it is under electric or mechanical field, and then if we divide this F A by the equivalent velocity u m, that gives me the corresponding damping. So, by doing that the final expression of C equivalent comes as 12 mu L B D divided by d square multiplied by 1 minus delta bar multiplied by 1 plus delta bar by 2. Now, we know that C equivalent for the inactive case, that means when we did not have the electric field applied, was C equivalent 0 multiplied by C equivalent 0 equal to 12 mu L B by D. So, this is the damping coefficient under no field, and this is damping coefficient under field, which we can call as active mode. So, here we can see that when we have this delta bar equal to 1, that means our yield stress is sufficiently high to block the flow. In that case, our active damping coefficient is going towards a infinite value. So, with those we can represent C q active in terms of C q 0, and the expression is C equivalent 0 divided by 1 minus delta bar whole square divided multiplied by 1 plus delta bar by 2. Now, let us define a number called Bingham number. And the Bingham number is defined as B I, which is equal to tau I multiplied by d divided by mu u m. So, tau I is the yield stress, and we can see that this quantity mu u m by d, that is also of the dimension of stress, and that is viscous stress. So, it is basically a ratio of yield stress and viscous stress, and that quantity finally comes to be tau I d by mu 12 mu L divided by delta P d square multiplied by 1 minus delta bar whole square multiplied by 1 plus delta bar divided by 2, and that can be written as 6 into delta bar divided by 1 minus delta bar whole square multiplied by 1 plus delta bar by 2, and the ratio of the active damping coefficient divided by the damping coefficient under no field can also be written in terms of Bingham number as Bi divided by 6 delta bar. So, this was about the flow in the valve mode or flow mode. So, we have seen 3 different regions, we have to treat them separately, and they have some conditions in between them which we have to satisfy, and finally after satisfying the condition we get the velocity profile, and then we, after getting the velocity profile, we apply the same approach, we find out a equivalent velocity, and from here we found out equivalent damping, and then we see how the damping equivalent damping coefficient changes when there is some electric field applied as compared to when there is no electric field. So, with that I would like to conclude this lecture here. Thank you.